Okay, basic integral rules. So chapter 8, everything you want to know about integration. We've seen a lot of this stuff already. I've kind of thrown you in the deep end already. But let's just take a look anyway. So sine inverse x, tan inverse x. We want to know the integrals associated with those characters. So what? Well, the integral of du all over, what was it, the square root of a squared minus u squared is going to be sine inverse of u all over a plus c. And then the integral of du all over a squared plus u squared is 1 all over a tan inverse of u all over a plus c. Hey. Okay, so we've seen those before. I want you to have those memorized. They are very common. Okay. Let's move on. Right. So we've seen these. Great. Maybe we can look at something else. So one thing the book takes a look at are 3 similar integrals. So you kind of study these things and find patterns, which is a lot of fun. 3 similar integrals. Okay. So here's the guys. The integral of 4 all over x squared plus 9 dx will be the integral of 4x all over x squared plus 9 dx, and then the integral of 4x squared all over x squared plus 9 dx. Great. So are they all the same? You know, it's kind of like when you are dealing with maybe a polynomial, a first degree versus a second degree polynomial versus a third degree polynomial. You know, are these polynomials related in some way? Who knows, right? So anyways, let's take a look at them. So here we got 4 all over x squared plus 9 dx. Okay, great. This guy is a tan inverse form, right? So it's doesn't look clear to you. We could, identify the a value as 3. In this case, u is just plain old x. So du, we could replace it with a dx if you want to put it into this exact form. Probably want to factor out constants. That's always a nice thing to do. And then we have dx all over if you want to rewrite it so it looks perfect. And 9, which is our a squared plus x squared. And then it'll be 4 times 1 all over 3 tan inverse of u all over 3, x all over 3, right, plus c. So this guy is turning into a tan inverse, 4/3 tan inverse of x over 3 plus c. Okay. Oh, yeah. So, okay. Part B then, let's look at this character. 4x all over x squared plus 9. Again, a good, safe thing to do is to factor out the 4, the x squared plus 9 dx. This guy, though, looks like it's going to be a natural log, right? You got to do a u sub for x squared plus 9. du is 2x dx, so I'm going to replace my dx with du over 2. It's my Intel box. Right, so I have 4 integral of x all over x squared plus 9, I'm replacing with u. dx I'm replacing with du over 2. Factor out the 1/2, I'll have 4 halves, so I'll have 2 times the integral of du over u. That's our natural log integral, so I'll end up with 2 ln absolute value of u plus c. And then this will just be 2 ln absolute value of x squared plus 9 plus c. Okay? Okie dokie. So anyways, the third one, let's look at that guy. See how that one pans out for us. the integral of 4x squared all over x squared plus 9 dx. Okay, this time I think I'm going to do some long division. Okay, so I know the degrees of the numerator and denominator are the same. Let's go ahead and divide 4x squared by x squared plus 9. So what times what is 4? What times x squared is 4x squared? Well, obviously 4, right? So 4 times x squared is 4x squared, and then 4 times 9 is 36. Subtract away. The end result, when I do my subtraction, is negative 36. Okay, so I can rewrite my integral in that way. So I'll have the integral then of 4 minus 36 all over x squared plus 9 dx. Right. The first part of the integral, so the integral of a difference is the difference of the integrals. I can integrate this guy. That's just 4x. Then minus 36 integral of 1 all over x squared plus 9. Well, that looks very familiar, right? That's the integral from part A. So I end up with 4x minus 36 times 1/3 tan inverse of x thirds plus c. So this is 4x minus 12 tan inverse of x over 3 plus c. Okay, so you can go back and kind of take a look. All right, there's some patterns or stuff there. Maybe an interesting part, which isn't as interesting to me as it used to be. The computer programs evaluate these things, right? And they don't necessarily do it in the same way that we teach you how to do it. When I was reading the computational math book, it was like they change everything into logarithms and then integrate that way. So for instance, and this is just to the side, this isn't in the book or anything, but if you have the integral of dx all over x squared plus 9, the real reason why we can't kind of use logarithms here is because we can't factor this over the real numbers. You have to go into the imaginary numbers and you get stuff like x plus 3i times x minus 3i, and then you have to do this thing called a partial fraction decomposition and change it into two different integrals, x with x plus 3i in the denominator plus some other fraction, x minus 3i in the denominator. Okay, and then you could use your rules for logarithms to integrate these, and they're going to end up being something like a ln absolute value of x plus 3i plus b absolute value of x minus 3i plus c. So computers are much more PDF oriented, partial fraction decomposition oriented. They'll always kind of just take these things apart, and then you'll get logarithms. Back in the day, it used to be an issue because you get an answer with, I guess, your calculator, and it wouldn't be in terms of arctan or something. For me, it was an issue because I got during the transition between computers and non-computer sort of work. I got a lot of students that were using their cell phones to do their integrals, so I would get these funny kind of written solutions, and I got interested, why is a student giving me these kind of solutions? And it's because that's how the computer thinks, and they were basically copying down what the computer was doing. It's obviously it's more advanced now. The computers will just give you a step-by-step as a human would do it, and if you wanted to, you can cheat that way. But anyways, so just neither here nor there. Arctans are actually just logarithms as well. So as you look back through your kind of looking for a pattern, and you have logarithm, then inverse tan. So it was inverse tan, then logarithm, then inverse tan. And you're wondering why it's going back and forth. Well, it really doesn't go back and forth, right? It's always a matter of logarithms. It's just instead of us humans, we will use this tan inverse formula as opposed to these logarithm formulas. I think, that was all my own research, which I pass on to you. So anyways, there's that. Let's move on. Okay. separate. So we have a bunch of basically checks that you do when you get stuck for doing your integrals. And you can code this into like an artificial intelligence program. If stuck, then try this. You know, so in particular, if you're stuck and you have a fraction, try separating it. So 37, we have the integral of a fraction, 1 plus cosine alpha all over sine alpha. So you could code your computer to kind of look for a fraction and then see if the numerator can be separated over the denominator. So it's the reverse of finding a common denominator, right? So in class, I've been calling this butterflying it or filleting it. So I'll end up with 1 all over sine alpha. That's my alpha. It kind of looks like a 2. D alpha plus the integral of cosine alpha over sine alpha. D alpha. 1 over sine alpha is the integral of just cosecant alpha, d alpha, and then plus the integral of cotan alpha, d alpha. We have formulas for these. They're not as well known as some of the other formulas. The first guy, cosecant alpha, you're going to have to multiply top and bottom by cosecant plus cotan or something like that. And so you're going to, with an ln of that thing, in particular in this case, it'll end up being negative because of the u sub that will result. Negative ln of cosecant alpha plus cotan alpha. Then this guy is kind of a sub for sines. So you'll end up with a 1 all over u. So it'll be a natural log as well. And it'll be the ln of the absolute value of sine of alpha. Okay, and then plus c. Okay, so yeah, separate if stuck and fraction, then separate, right? Here's another one. If you have a polynomial in the denominator, try completing the square. Okay? In particular, if, so you can almost write conditionals here, if polynomial and, so how do they do that in coding, right? They use the ampersands and quadratic, so degree of your polynomial equals 2, then complete the square, right? So I don't know, I don't really code all that much. So complete square, maybe have a complete the square function, right, of the polynomial that you're working with. So anyways, right, let's look at 45, I guess. So 45, we have the integral of 4 all over 4x squared plus 4x plus 65 dx. And I don't know how to integrate it, so I'm going through my if-thens, and I come across this thing, completing the square, so I'll try that. So in the denominator, to complete the square, I really need a leading coefficient of 1, right? So I factor out a 4, and I get x squared plus x. And then I want to complete the square, and then whatever I add in, I have to immediately get rid of it. So I'm going to have to get rid of it somehow. And then I still have this plus 65 thing floating about, dx. Right? Alrighty then. So I got the integral of 4 all over 4 times x squared plus x plus this thing. So what is that thing? It's always b all over 2 squared. So it's 1 all over 2 squared is 1/4. Then I have to immediately subtract the product of 4 and 1/4, which is 1. So I'll be going -1 here. Right? And then you have 4 times x plus 1/2 squared plus 64. Dx. Okay, we can simplify the denominator a bit. This will be the integral of 4 all over 4 times x plus 1/2 squared plus 16 dx. And then we can remove this multiple here, this factor of 4, and we end up with dx all over something that looks like an inverse tan. Right? In particular, our a value is 8. Oh, sorry, that should be 16. So our a value is 4. And then our u is x plus 1/2. And of course, then du is just dx. Okay? So we can rewrite our integral as du all over u squared plus 4 squared, and then dump it into your tan inverse formula. So we would end up with tan inverse of u all over 4. So 1 all over, sorry, so 1 all over 4, tan inverse of u all over 4, and then plus c. So this would be 1/4 tan inverse of x plus 1/2 all over 4 plus c. Okay, so another one then, if too lazy to do long division, then add and subtract terms in the numerator. Okay, what? So add, subtract terms in numerator. Okay, so anyways, we have this integral 23 where the numerator's degree is higher than the denominator's degree. And you could do long division here. There's no issue with that. But sometimes a little quicker to just pull this trick. Subtract 1 and immediately add it in the numerator. And then you can bifurcate, or what do we call that? Butterfly it. And you end up with two integrals now, x squared minus 1 over x minus 1 dx, and then plus the integral of 1 all over x minus 1 dx. Okay? You could simplify this then by factoring x squared minus 1 as x minus 1 times x plus 1 all over x minus 1 dx. Plus this guy is just a natural log, right? So if you did a u sub for x minus 1, du would just be dx. Okay, so I don't have to worry about any constants or anything. It would be ln of absolute value of x minus 1 and then plus c. X minus 1's divide out. I have the integral of x plus 1 dx. And then plus ln of absolute value of x minus 1 plus c. Integral of x plus 1 is x squared all over 2 plus x, and then plus this ln absolute value x minus 1, and then plus c. All right, what else can you try? What else can we think about when we get stuck? Conjugates are always a good idea. One type of conjugate you're probably not as familiar with working with are the Pythagorean conjugates. So the deal is, if you have something like 1 plus cosine theta floating in your integral somewhere, supposing you multiply it by 1 minus cosine theta, you can condense this into a single term using the Pythagorean identities. So they call it a Pythagorean conjugate. Okay, so if you were to multiply this out, you would get first is 1, then outer negative cosine, inner positive cosine, those add away, and then minus cosine squared theta. Okay, of course, 1 minus cosine squared theta is just sine squared theta, so this becomes a way of taking two terms and making them into one. Okay. So common techniques for trying to unlock integrals, two terms in the one term in the two, stuff like that. So let's say 71 in particular. We have the integral of d theta all over 1 plus sine theta. As it sits, there's really no way to attack it. You can't really do a u sub without sort of introducing a floating term in there. So what you do is or rather multiply top and bottom by 1 minus cosine theta, right? So if you have 1 plus sine theta, multiply by 1 minus sine theta, and you'll end up with 1 minus sine theta all over 1 times 1 is 1, and then the outer is negative sine, the inner is positive sine, and the last will be minus sine squared theta, d theta. Okay, so why do I do that? It's because now I can condense this into one term. 1 minus sine theta all over 1 minus sine squared is the same as cosine squared. Right? And then you can butterfly. Okay? So we'd end up with the integral of 1 over cosine. 1 over cosine squared is the same as secant squared. So we have secant squared theta d theta, and then minus the integral of sine theta over cosine squared theta, which is the same as sine theta over cosine theta times 1 over cosine theta d theta. The integral of secant squared is just tan, so I get tan theta, and then minus the integral of sine over cosine is tan theta, 1 over cosine is secant theta d theta, and tan secant is just the derivative of secant, so we end up with tan theta minus secant theta plus your integration constant. Okay? Okay, that's pretty much the tall and the short of it. There are other miscellaneous, let's just look at one sort of generic integral that doesn't seem to really follow a pattern. So u subs, you know, is pretty much what the rest of these are about. Number 6, just a miscellaneous type problem. You have 41 is the integral of tan of 2 all over t squared dt. Okay. So your familiarity with the derivatives of functions is important in order to evaluate these guys quickly. So if you know the derivative of 2 over t is kind of like negative 2 over t squared, it's like when you take the derivative of fractions, it increases the denominator. When you take the derivative of something like t cubed, it will decrease the denominator. So anyways, when you do a u sub for 2 all over t, which I'll rewrite as 2t to the negative 1, you'll get du is negative 2t to the negative 2 dt. And then this part of it is going to cancel with the t squared, and we'll have something that we can integrate, right? So anyways, solving for dt, that's going to be negative du, or it's actually negative t squared all over 2 du, right? If you multiply both sides by negative 1/2 t squared, you'll end up with this. Okay, so what do we got? We got the integral of the tan of u all over t squared times negative t squared all over 2 du. You can factor out then a negative 1/2. And you get the integral, the t squares cancel, the integral of tan u du. And then the integral of tan is just the ln of the absolute value of secant. And then back substitute, and you are out of here, right? So negative 1/2 ln absolute value of 2t to the negative 1, secant of that, sorry, so it's equal to negative 1/2 ln absolute value secant of 2 all over t plus c. And that's it. Okay, thanks for watching. See you next time. Bye.